Wild Health is about optimizing you. We use genomics, blood work, biometrics, microbiome assessment, many other tests, and a conversation with you to come up with a full health optimization plan. What's the perfect diet, exercise, and supplement plan for you and only you? The Wild Health podcast is about optimizing all of us. Here we cover the cutting-edge science that gives you the base to be able to apply the personalized plan we give you as a patient. To sign up as a patient, go to wildhealth.com. Or if you're a physician or health coach and you want to learn how to do this for your patients, we're happy to help as well. Wildhealth.com for all the information on becoming a patient or working with us.
So very excited to have Dr. Neil Theise with us on the podcast today. Neil is a professor of pathology at the NYU Grossman School of Medicine. Through his scientific research, he's been a pioneer in adult stem cell plasticity and the anatomy of the human interstitium. He's also a longtime student of Zen Buddhism. Neil's studies in complexity theory have led to interdisciplinary collaborations in fields such as integrative medicine, consciousness studies, and the science-religion dialogue. He lives in New York City and is the author of Notes on Complexity, a scientific theory of connection, consciousness, and being. And as you'll hear, he was also my mentor in medical school. So let's get into it. Okay, Neil Theise, Dr. Neil Theise. I don't think I've been more excited for a podcast since we started podcasting. So no pressure. You don't have to deliver. This is just all personal, as you probably already know. So for listeners,
I taught this guy.
Neil was my mentor. So Neil was my was the first physician teacher, professor of pathology at NYU at the time when I was a medical student a million years ago, who was a real person to me, right? Was not just like somebody in a white coat telling me that I should do something better than I was doing it, or that I was, was a human being who interacted and treated me like a human being. And while, no offense, I never was going to go into liver pathology as a clinical career, and I know you're not offended. I'm not. I can't thank you enough for doing that, for just being the first human person in medicine who was kind. So I'm forever in your debt for that.
I actually, when I have to reminisce slightly, the way I think, if I remember correctly, the way we started talking one-on-one is because I inserted into the liver pathology lectures an annual lecture about how to talk to your patients about sex, because it wasn't in the curriculum as yet. And, and I think at that point you thought, oh, maybe I can talk to this guy. And then you went on to start doing activist stuff. I think you were doing needle exchange through Bellevue.
Yeah, I was working in needle exchange, and we also I think we overlapped because we started doing volunteer work where we were doing hepatitis A vaccination for injection drug users who, just because for listeners who aren't familiar, the risk of serious liver failure if you already have hepatitis C from, say, injection drug use, and then you get a co-infection with hepatitis A, can be so high. We started doing a voluntary hepatitis A vaccination program. I know we leaned on you for some advice back in the early day, but that was student run and was definitely something that I was into.
And the reason I bring it up is because when I reminisce at people about some of the stuff I enjoyed most in my medical career, it was teaching the medical students and teaching them that, which usually came as a surprise because they were expecting a lecture on something else. And your year was the group of students that most heard what I had to say and sort of leapt to it as a challenge with some kind of excitement. So I actually occasionally am telling people about you as an example of things I'm most proud of in my teaching career.
Wow.
So there you go.
Thank you for that. The way that we got reconnected, I think, is also just like beautiful, universal serendipity. So Julia Priest, who's one of our health coaches at Wild Health and a friend, sent me a text message while we were in California last month. And the text message was just a link to a podcast, and no text from her, just the podcast link. And I opened it up, and it was you on Armchair Expert,
Right.
Which is one of my wife's favorite podcasts. I didn't even look at it. I just hit play because I was walking, and as soon as I heard your voice, I was like, "Oh, what?" And it turns out that in the interim, you have done a ton of things, but amongst them, outside of publishing in Nature and Cell, and discovering key things about how our bodies work at a core level, you just wrote a book which is phenomenal that everybody should go and pick up like today. Notes on Complexity: A Scientific Theory of Connection, Consciousness, and Being. And I don't know if we'll have any video snips, but I'm holding your book. And I read this in one sitting, and I'm not saying that to make you feel good. It's captivating. It's just scientific enough to satisfy folks who have somewhat of a science background, but totally like layperson accessible, and the ability to weave together science and consciousness into what's essentially maybe the closest thing to an answer around the hard problem of consciousness is like incredible. And the fact that it just came as like Julia sent me a text and there you were, and in the interim, by the way, here's this book. So it's just a crazy way to reconnect, and for listeners, we've already blown a half an hour of our time before we hit record, just catching up, and you're lucky / maybe unlucky to have like two tattooed Jewish doctors chatting about consciousness. So that's what you're in for. So let's get into it. Let's just get into it.
Let's do it.
Complexity theory. If you ask ChatGPT to tell you what complexity theory is in 2 sentences, it does a pretty decent job.
Tell me. Maybe I can memorize it and use it.
I'm gonna see. I'm not gonna put you on the spot and ask you to say it first. Let me see if I have the notes. Here you go. So, complexity theory is a field of study that examines how simple interactions between components within a system can lead to complex overall behavior that is often unpredictable and nonlinear. It explores the emergent properties and intricate patterns that arise from these interactions, focusing on how small changes can have significant impacts on the entire system.
Yeah, that's pretty good. It's better than I usually do.
It's not bad.
No, it's not bad. I mean, that's been, when my editor first read my first draft of the book and said, "Yeah, but you need a chapter at the beginning saying what complexity is." I'm like, oh. So, and figuring out what to say. I mean, what you read to me, that's pretty specific. But does anyone listening to it have any idea what kinds of things they're talking about?
No.
No. And so, I've found very long and very short versions of it. I still don't have an elevator pitch. What I'd say, and sort of what's chapter 1 of the book, is that complexity theory is the science of how living things arise in the universe, how they interact with each other to create larger living things, such as cells interacting to become bodies, and how they further self-organize into larger scale structures that are social, like neighborhoods in a city, a colony of ants, a flock of birds, economies, markets, the global ecosystem, Gaia, etc. And so it's really a scientific theory of life, and we think of that usually as biology. But the difference between biology and complexity is biology is all about what we do in the hospital and in the laboratory in Western medicine. We take things apart. We take the clock apart to see what the pieces look like, and then we know that if we put the pieces back together again, you get a clock. So biology takes bodies apart and you get organs and tissues, and then you take those apart and you get cells, and you take those apart and you get molecules. And so we have cellular biology and molecular biology, but they don't get put back together again like a clock. You can't take these cells and just, we call cells, we often call them building blocks, but that makes them sound like blocks that you stack into a structure, and you can't do that with cells. You put them in a dish and they interact with each other and they do make things. But some of those are tumors, some of them are something we've never seen before. We're learning to build new organs from them, but that's, in the very beginning stages. But it's about cultivating things. It's not about engineering things. So there, I just went off on a toot like I do. But the basic message of which is complexity theory doesn't describe machines. Living things are not machines. Machines always behave exactly the same way. They are predictable. And living things are never predictable. And as your ChatGPT definition included, that unpredictability is a hallmark of life.
Yeah, and it seems like there's a sweet spot of randomness.
Mm-hmm.
Right?
Yeah. And so what you're referring to is what I discuss as the 4 rules of complexity in chapter 2. And you can discuss them in any order, though starting off with that low-level randomness thing is not the easiest place to start. Shall we go through those? And
yeah, let's go through.
And then we can make things concrete, so your listeners will know exactly what we're talking about. One of the pleasures I've had of talking about complexity for the last, it's going to be close to 25 years now soon. This book is really the sum of stuff I've been talking about for that long in both in academic settings, medical centers, grad students, med students, but also at yoga centers, Zen centers. My nephew's 5th grade class had me come in and talk about it. And everybody, the common experience coming out of these talks, I've gotten feedback from all these different audiences, is that once I give them what these 4 rules are and give them some examples, they walk out into the world and they see it everywhere. Mm-hmm. Because complexity describes everything around us in our world, really. So, one of the things that, the way I was introduced to it, back when I was teaching you, I was starting to do stem cell research, and I was paired off with an artist. We got a grant. A friend of ours got a grant to bring the 2 of us together just to explain to each other what we do, because the people who were funding it wanted to see how artists and scientists might communicate. And so that was a very nice off-kilter kind of thing I got to do, and I got to meet this woman named Jane Prophet, who's an artist. And I was explaining to her what I do with the stem cell research, and she said, the way you're talking about stem cells, it sounds to me like I've been working with some people in complexity theory, she said, and what you're describing sounds like the way they talk about ants and how ants build a colony, but you're talking about cells building a human body. And I said, what's complexity theory? And we were sort of off and running. And the ants making ant colonies is a really good example of all this stuff, partly because there isn't anyone who didn't spend time playing around with ants when they were kids. Anywhere in the world there are ants, and growing up, people see ants. So one example, rule number 1, in the order I present them, is that numbers matter. How many ants you have determines how complex their interactions become and how complex the colony becomes. But if you don't have enough ants, you don't get any interactions that build a colony. And I know this because my nephew, who was in 5th grade at the time, that's how I got invited to a 5th grade class, thought I was obsessed with ants. So he got me an ant colony. And like we used to, in my generation, we used to order them from the back of comic books, but now you just get them on the internet. And it's an ant farm, 2 clear panes, and in between them there's sand or a gel, and 25 ants, and the ants dig tunnels, and they build food lines, and if an ant dies, they put it over in a corner that becomes the cemetery. And those three structures, there's no ant in there who's planning where those tunnels go or how the food line forms or where the cemetery should be. Those happen out of the interactions locally between the ants as they encounter each other and the chemical signals that they lay down for each other that they can read. These are called pheromones. And 25 ants is enough to build that kind of complexity of a colony. But as they start to die off, somewhere around 5 or 4 ants, they're no longer interacting with each other. And they're just off doing what each of them does. There's no, we talk about them self-organizing into emergent structures, structures that emerge globally out of the system, out of these local interactions. But 5, 4, 3 ants, there's no global emergence. They just are individual ants going about their business. So if you don't have enough ants, you don't get emergence, you don't get complex self-organization. And if you have 250 ants, with the increasing diversity of interactions between them and the increasing numbers, then you get a more complex ant colony. And if you have 2,500 ants, you have a still more complex ant colony. And the amazing thing is that the math that describes this is the same, whether you have a small colony or a large one. And it's the same math that describes what happens if you have human beings living in a village. More humans, you have a city. More humans, you have a megalopolis. Whether it's colonies or humans interacting, it's the same math. And that same principle applies. The more numbers, the greater complexity. But you need a few. If you have 3 people wandering on the woods, you're not going to get a community. But you get 5 people, you start to see a social structure arising, right? So that's rule number 1. How complex a system depends on how many interacting individuals there are and how diverse the interactions are, the kinds of interactions they have. And, and you can see this in biology. You have single cell organisms that start to cluster into communities that eventually become multicellular organisms. And it's the same sort of thing. The same mathematics describing what happens at the cellular level becoming bodies is what happens at these other levels. And that immediately gets you into, we'll come back to boundaries in a little bit. The second rule is that the interactions have to be of a certain kind. They have to be what we call negative feedback loops or positive feedback loops. Not negative as in bad, positive good. Negative as in an air conditioner in your room. The warmer a room gets, the air conditioner turns on, and when the room starts to cool down, it gets to a set temperature at the bottom, and the air conditioner turns off, and then the temperature starts to rise again. And so this is a negative feedback loop that's continually keeping the room in an oscillating, what we call homeostatic range. And if you think about living things, if you think about our own bodies, homeostasis is what it's all about. It's not stability. Our body temperature changes from morning till evening. It's why fevers are worse at night and better during the day. But if you look at your normal body temperature, it's oscillating in a wave. Your hunger comes and goes. Your sex drive comes and goes. Everything comes and goes within a healthy oscillation. And that's normal biological functioning. But if you have a positive feedback loop, what we're talking about is something like if a room gets warm, a heater turns on. And the hotter it gets, the higher the heater turns on. So the room gets hotter and hotter and hotter. And this is sort of an unlimited, uncontrolled thing. And you know that that's going to be self-limiting. Eventually the fuel's going to burn up and the temperature will collapse, right? So you can't have too many of these in a biological system, in a living system, but you can have some. Think of how when you get an infection and you get a fever, that's a positive feedback loop and your body is getting hotter and hotter. But the result of that is your metabolism goes up, it improves the efficiency of your immune system, helps you fight off the infection, and when it does, the negative feedback loops come back in and start to lower your temperature and bring it back down into homeostasis. So you can have positive feedback loops, but negative feedback loops have to predominate. And that's rule number 2.
Yeah, it's almost like that negative feedback loop is still in place at the same time in parallel as the positive for your fever, for example, right? There is a max temperature at which point you need to your homeostatic range just got shifted from the positive feedback loop. But at the end of the day, the negative feedback loop is still gonna take predominance, right?
Unless you die.
Unless you die.
I mean, some people die of a fever, right?
Yep.
That can happen too. And we'll come back to the question of death because it's an important question.
So rule number 1, numbers matter, not enough, no interaction or limited interaction. And then as we escalate the numbers, we increase the levels of complexity. Rule number 2, you got to have negative feedback loops and positive feedback loops in terms of maintaining homeostasis.
And the negative feedback loops have to predominate.
And they have to predominate. Yep.
Yeah.
And then rule number 3.
Yeah. Actually, one more thing. Rule number 2, that you can get self-organization into larger global structures if you have a predominance of positive feedback loops. But those tend to be energy expending and self-limited. So think about cancer.
Yeah.
Cancer is a living thing, but it's governed predominantly by positive feedback loops. And so eventually you get rapid growth, explosive growth, but then the fuel runs out and you get collapse. And if you think about a person with cancer, they've got this tremendously proliferative, very alive thing growing in their body. At the same time, they're becoming wasted because it's just consuming huge amounts of money that their own metabolism can't support. And you see exactly the same thing in economic systems. This is what happens when you have an unregulated economy. Then, when you diminish the amount of regulation in the system below a certain amount, you wind up having recessions and depressions, sudden rapid economic growth, economic bubbles. And this happened before the Great Depression. And the legislature brought in the Glass-Steagall Act, which was negative regulating feedback, essentially, to limit what banks could do. And as these were eroded by both Democratic and Republican parties in the 70s, 80s, and 90s, what happens? You wind up getting economic bubbles leading to the Great Recession. Economic collapse, cancer of the economy, too much positive feedback, not enough negative feedback, so they bring in the Dodd-Frank rules, and that's eroded over the last administration. What do we have? Economic bubbles and another collapse. So we look at these things in the economy and we think in terms of politics, but the fact is it's the same mathematics that describes how cells become bodies, how ants become colonies, how humans create social structures, how our bodies function. These are mathematical, physiologic questions. They're not political questions, really. And this is one of the things that's important, I think, bringing complexity into people's awareness, is it changes how you analyze what's going on around you, potentially. So that's rule number 2. Rule number 3, I've already sort of mentioned that things happen because of local interactions. There's no ant standing above telling the colony how to organize. People may say, well, what about the queen ant? She just serves a reproductive function. She actually has very little to do with how the colony is run. She's just producing more ants for the next generation. And so you may think sometimes that, there's someone you're existing in a hierarchy and there's someone above who's controlling everything and dictating everything. And we sometimes in human societies have the illusion of that. We think we have a strong executive or an authoritarian leader who in fact is observing everything and running everything very tightly. But in fact, it's not a hierarchy, it's what we call a holarchy. everything is interacting with everything else at a local level. Even the president sitting in the Oval Office is having local interactions with the people who work for him, who talk to people on the telephone, who then talk to people through emails. These are local interactions, even though in our heads we think of them as higher up, hierarchical sort of things. And the only difference is perhaps the person we look at as thinking they're at the top, planning everything down below, what they really have is more connections to more nodes within the map of the system. But it's really sort of flatten it out in your imagination into this net. And there's always parts of the net they can't reach. And that's where insurgent parts of a political party arise. Or, I used this example talking to someone the other day. The Soviet Union collapsing, they had rigid top-down authoritarian control. And people thought, oh, there's a lock on how everything works this way and it's top down. Except apparently no one in the Kremlin was paying attention to what was going on in the shipyards in Poland. And suddenly you had the Solidarity movement arise out of nowhere and the whole system collapsed. So there's an illusion of top down in human societies, but it's always an illusion. Things are always going to be shifting from the bottom up. And so complex systems, most of what arises in terms of a global structure is a bottom-up sort of phenomenon. To get a feel of what that's like, particularly if you live in a city, think about when you're walking down a crowded sidewalk and you have people listening to, they have their earbuds in, or they're reading a book, or they're looking at their watch because they've got to get somewhere, or they're lost in their thoughts about the argument they just had at home or what's facing them when they get to the office. And they're all involved in all sorts of complex thinking and behaviors, and yet they're moving smoothly down the street in interweaving lines that don't bump into each other, don't knock into each other, don't get in the way. How does that happen? Because our bodies are actually monitoring things on the local level. How close we're coming to other people, what other people's footsteps sound like, what the sound of other people moving by is, and we have little adjustments of the angle of our shoulders and the way our feet go, and somehow it just self-organizes into smooth traffic, even though we think we're planning out our route to getting from home to whatever errands or office job you're headed to. And again, the same math describes it all. One of my favorite examples is I had the good fortune to hang out in Kyoto in Japan for a few days, and I was sitting in this beautiful, quiet Zen garden, and there was this wisteria growing up the side of where the bench was, and there was this one particularly thick branch, and there were two lines of ants going up on either side of the branch, and there was a single line of ants coming down the center. And I thought to myself, because I already knew about complexity, I thought, oh, look at the self-organization leading to this interesting pattern of ants going up on the outside and coming down in the middle. Ant after hundreds of ants doing this. And then I got home, and sometime in the next few days, home is New York City, and I was at the Essex Delancey subway station, and there's a staircase there that's particularly wide compared with most subway stations. And I was there at rush hour, and I got to that staircase, and there were two lines of people going up on the outside and one line of people coming down on the inside, exactly like the ants had done. But these were humans, and they were all busy thinking whatever they were going to be doing.
Nobody telling them. There wasn't a traffic director saying, "Hey, down on the sides, or up on the sides, down in the middle," just immediately arising spontaneously.
Yeah. So this is what I mean by bottom up, from local interactions, and that's rule number 3. And then rule number 4 is what we come to. You mentioned the limited degree of unpredictability or randomness in the system. So if the interactions between ants, let's say, is completely random. They don't have any set way to interact with each other. There are no rules for how they respond to different signals or communications from the other ants. Then you don't get any self-organization. You just have ants running all over the place. Anarchy. But if you have too little randomness in the system, then it's going to be machine-like. It will always be doing exactly the same thing. And this is a good example of this is a food line of ants. So if you see a food line of ants, it looks like a straight line between, let's say, a sugar cube and the colony. And they're very efficiently picking apart the sugar cube and carrying the bits back to the colony, and then go back out and get some more. And the way they form that line is through, as I said, pheromone signals that tell the ants, hey, I'm carrying some food. The food lies that way. Go follow the trail I just laid down. You'll find it. And then they turn around and follow it back to the colony. But if you bend down and look closely, there's always a few ants that aren't following the line. It turns out that these are the ants that if you put your foot down in the middle of the food line, these ants are the one, not in the food line, are the ones that very rapidly establish a new route for the food line around your foot. And in fact, the most efficient route. Or these are the ants that are finding another food source even before this one has run out. So when it runs out, there's another food source and another food line getting established. So there's always a continual supply. So it's this low-level randomness that allows for creative adaptation to a changing environment, either the ebb and flow of food sources or an obstruction coming down like your foot into the middle of a food line. If there are no divergent ants, if there's no randomness in the system, then you bring your foot down into the middle of the food line. There's no way to find a new route around your foot. There's no one to do that job. If everyone is following the food line, when the food source runs out, where's the next food going to come from? So you need this low-level randomness in the system. And this goes, again, for any complex system, whether it's humans interacting, cells interacting, flocks of birds, etc. One of my mentors, and a friend of mine, who's one of the founders of complexity theory, and probably the guy who's most written about its implications for biology, for life in general, his name's Stu Kaufman. And he talks about this low-level randomness and unpredictability in the present moment as being the adjacent possibles for what the next moment can be. And that one of these adjacent possibles will be selected depending on how the environment changes in the next moment. And then the system organizes, it takes a step forward, and a new array of adjacent possibles happen. And I just love this idea that if you're a living being, let's say each of us, then there's an array of possibilities for what the next moment might have. What opportunities you might have, what dangers you might have, what possible responses you might have. And there's no predicting with absolute authority what the next moment will be. Machines are not living things. Living things are not machines. Humans are not machines. The living world is not a machine. The universe containing living things is not a machine. So this idea that we've inherited for the last few hundred years, from Newtonian mechanics on down, that if we knew what everything was doing in the world at this moment, we could predict the next moment, that's a fallacy. Once life comes into the system, it's always unpredictable. You can talk about probabilities, you can talk about tendencies, but you can't predict. And you just look at, everything that's happened in the global political scene for the last 8 years. I mean, if we ever thought we had an idea that we knew what would happen, it's clear we have no idea.
Yeah.
But there's great opportunity in that as well.
Yeah. Yeah, I mean, I'd be interested in your thoughts on this. I read that, the section in the book around randomness, and I thought of it as like not just even a sweet spot for randomness, but almost like it's like life's mathematical constant.
Except
right?
even that's not.
It's
constant.
still wiggly. It's still wiggly, but there's that range of randomness.
It's
that
not
allows
infinite.
everything to happen.
It's not infinitely random. It's not an infinite range of possibilities. It's a constrained degree of what can happen in the next moment.
Yeah, almost like our body temperature.
Yeah. Now, one of the implications of this, so we'll come back to the math, and this is mathematical as I'll get, because I'm not a mathematician. And, while complexity is all about, you study it by running elaborate computer models on very fast machines. It's why computers had to be invented for us to discover complexity and make a theory about it. But we can talk about complexity as it being a kind of order in the universe. And so what do I mean by order? So you can have rigid, perfect order. Think about water molecules in an ice cube, and they're all stacked up exactly the same way, and the distances between them you can measure, and you can even write geometric equations to give the structure of an ice cube. So that would be perfect order. Then there's complete disorder, like molecules in a gas, completely randomly bouncing around. And then you have what's called chaos. And many of your listeners are probably more likely to have heard of chaos than they have of complexity theory. And this is described by fractal geometries, which, again, they're sort of in the popular imagination. If you search the word fractal, you see these incredibly filigreed, multicolor, usually, images that the hallmark of them, no matter how close in you get, it just looks like the same thing. And we see chaos and fractal geometries present in nature too. So think about a tree trunk, and as it branches, it goes into two separate branches, but those look like tree trunks, and those separate into smaller branches, and those look like tree trunks, and they separate and separate. And we know there's a limit. Eventually you get to the leaves. But if you don't know how close you are into the tree, if someone takes a picture of just the tree and eliminates all background, you can't tell if you're looking at a trunk, a large branch, a small branch, because it all looks the same, no matter how close in you get. Mathematically, that's infinite. It doesn't come to an end the way a tree branch does. And you can think about, puffy clouds are the same thing, or the jagged edge of land at the edge of an island, for example. It looks the same from a satellite, but you can go in up close and look at sand on the beach, and the jagged pattern of where the land meets the water is actually kind of the same. So that's chaos and fractals. And another example of how this exists in biology, if I show you an image of the Mississippi River going into the Delta, the Mississippi Delta from a satellite, and I tell you this is the Mississippi Delta, you'll nod your head and go, okay. But if I tell you, oh, this is an image taken by some special imaging device of blood vessels and capillaries in the human body, it looks exactly the same, and you'll believe me. So you see the same fractal nature of things in living systems as you do in the natural world, even in non-living things. So we have order, disorder, and we have chaos. Complexity was the last to be discovered, and mathematically it turns out that complexity lies at the boundary between perfect order and chaos. Not chaos as in complete anarchy, but chaos as in fractal geometries. Mm-hmm. And so it's a mathematical zone. So I thought when I first learned about this that, you could probably mathematically describe any living system, any complex system, as a specific mathematical point in that region between complexity, between chaos and order. And people, the phrase was coined that complexity arises at the edge of chaos, or life arises at the edge of chaos, meaning this boundary. But it's not a distinct boundary between order and chaos because chaos is fractal. So you have this infinite filigree, can get smaller and smaller and smaller, ever finer at that boundary. And because of the low-level randomness in the system, it's not a specific mathematical point where you would plot a complex system. It wanders around in this region. And given enough time, inevitably, it will stumble out of this region either into rigid order that's non-adaptive and machine-like, or into chaos, which is non-living. And you get a mass extinction event, either of a part of the system, I had a couple of little minor strokes back in February, so I had a couple of little mass extinction events in my brain. I'm doing fine, but these things happen. Or eventually we all die. The low-level randomness that gives us the ability to creatively adapt and survive as the environment changes around us, the very thing that makes us able to be alive, also means that inevitably, eventually, there will be a mass extinction event and you'll die. So there's no such thing as a fountain of youth, there's no such thing as eternal life, because what makes you alive necessitates eventually dying. And suddenly you have this mathematical theory that has stumbled right into issues of philosophy and meaning and what it is to be alive, what it is to be human. And it's coming right from the math, which is one of the crazy things about complexity to me.
Yeah, I mean, it's a great transition to, I think, sort of the latter half of the book, and the really, we don't need to stick with the trajectory of the book exactly. I know you've had a regular and pretty detailed Zen practice for years and years, predating your interest in complexity theory.
Oh yeah,
even.
yeah. That goes back to when I was in college, high school.
And I'd love to hear sort of where your head's at now around
Sure.
the intersection between complexity theory and being or consciousness.
Sure. So the idea of bringing together or finding some meeting points between my spiritual interests, which started out as I was I came from parents who were first generation Americans from Europe. My dad was a Holocaust survivor. My mom's family was from England. And I was brought up in a fairly observant Jewish household, though it was a very warm, not burdensome thing in our community of Holocaust survivors, I think largely because our parents all looked at us as the hope for the future. So there was something joyful about the Jewish community I arose in, which was not Orthodox, but more observant than most of the surrounding American Jews in West Hartford, where I grew up, and in New England. But I had this looming issue as I had my spiritual life as a practicing Jew, as a kid. I believed in God. I had a prayer relationship with God. I had stuff going on that I was interested in exploring. But how do you put that together with the Holocaust? This was kind of a glaring problem for me to face. And at some point in high school, I found that there was such a thing called Jewish mysticism, and that mystical practice was about a human trying to have so close an identification, an experience of God, that almost a unification with God. And I thought to myself, oh, if one could achieve that state, you could see things with the God's eye view, and then maybe from the God's eye view there was some way to make sense out of things like the Holocaust, out of human suffering. And so that was my instinct. And now I was a nerdy kid, and at that point I was already reading about quantum physics and relativity. Einstein was my hero. I used to celebrate his birthday every year, which is a little annoying. But, in fact, I still was doing it, I think, when I was teaching you in medical school. It came to an end soon after. But I have other feelings about Einstein now, but that's a whole other story. And so I had this scientific interest, and I had this metaphysical interest, and those two things were separate. And the question of Jewish mysticism wasn't available to me as a middle-class gay kid from New England. You had to be at least Orthodox and married and, been studying in religious schools to access that stuff in the Jewish world still at that time. But I found myself exposed to Zen Buddhism and Zen meditation, and I thought this was a Didn't feel like it was in too great a conflict with my Jewish practice, and so I started meditating as a Zen Buddhist. And I became a formal Zen student. I had a daily at-home practice and blah, blah, blah. When I started doing the complexity theory stuff, what I've already described has some interesting implications. And this is where I started to get really excited and where my talks actually started coming from. So I've already said that you can be walking along the desert floor and you see a dark shape in the distance and you see that it's moving a bit, but you think that it's a thing. And then you go up close and you see that it's not a thing at all. It's an ant colony. What looked like a thing closer up looks like an interaction of smaller things, just a phenomenon. But I've already implied that if you go up to the ant more closely, or the bird in the flock, or my finger pointing at the bird or the ant, then the body disappears too into self-organizing cells. At the microscopic level, our bodies are cells. They're not actually things. And they're not only our human cells, they are our microbiomes too. The bacteria and viruses and fungi, it's mostly bacteria that cover the surface of our bodies and line all the crevices of our bodies. And we know that we leave bits of our microbiome around whenever we touch anything. If we kiss someone on the cheek, if we grab a doorknob, if I touch my mouse on my computer, my mouse pad, we're leaving bits of ourselves behind. And I say ourselves because without those bacteria, you are not a living, healthy human. You'll be dead within a short amount of time if you were to completely sterilize yourself. Just think if you overdry your hands from hand sanitizer, how your skin starts to crack. And then you're going to get an infection. If we didn't have antibiotics, you'd be dead soon. So at the cellular level, where's your boundary? If you look at the microbiome of people who share a home, including their pets, it turns out there's a single microbiome that is one large complex system that's a living thing that has its islands of human, cat, and poodle. But at the cellular level, our boundaries are actually farther out than the boundary of our skin, which it seems to be at the everyday scale. Are cells a fundamental unit? No. They're just molecules floating in water. And we know that we breathe in molecules from the world outside, and we breathe out molecules that are fuel for the plants, oxygen and carbon dioxide passing between us. So where are our boundaries at the molecular level? It's the whole biomass of the planet. You're seamlessly intimate with the entire biomass of the planet. At the atomic level, your boundaries are, there's no atom in our bodies that we haven't breathed, eaten, or drunk from the planet. So are we these living things that are sitting on top of this rock we call Earth, worrying about how isolated we are from each other? Or are we the atomic substance of the planet that in 3.5 billion years has self-organized into beings that think of themselves as separate? But in fact, our boundary is the entire planet. And then you go down to the quantum realm, and non-locality and entanglement, won the Nobel Prize last year or the year before. So at the quantum level, the universe is one seamless unity. So that's where complexity takes us. One morning I was going to the Zendo and to lead the morning sit, and no one else showed up that morning. So I opened the Zendo, I lit the incense on the altar, and I was just sitting there. And this was when I was doing stem cell research, and I was thinking about complexity theory and stem cells and cells moving around the body. And I was supposed to be doing my Zen meditation, but instead I was just caught up in this question of my body. Is it cells or is it my body? Which is it? And I had an experience a few days before where I was at a street corner in New York, and I was obsessing about this notion of my body as cells, and the street light changed, and the people who were on the corner with me stepped off to cross the street, and I was so into this vision, this sense of my body being made of cells that I couldn't step off because my leg had become a flock of cells and I couldn't move it by direction. And then I suddenly realized what had happened and I could walk again. So here I am in the Zendo, and I'm sort of sinking into this same feeling. And at some point during this, I looked up across the room and I saw the incense stick turning into smoke. And which is it? Is the incense stick or is it the smoke? Is my body cells or is it this bounded body? And I suddenly couldn't tell the difference and realized neither was the answer, but both were correct. And in that moment, I had a direct experience of what in Buddhism they call the emptiness of inherent existence. That something appears to be a reifiable thing, an entity, something solid that you can depend on, like a human body or a stick of incense, but only from one perspective. And there's always another perspective where it becomes the smoke, it becomes the community of cells. And that was... I always get choked up when I tell this story. It was an experience. It wasn't a concept. That the nature of existence depends on your perspective. And this is what the Buddhists meant. And it wasn't a metaphor. It was a fact. And I took this to my Zen teacher in one-on-one interview, which is how teaching happens in Zen. And I said, is this what's meant by emptiness of inherent existence? And she goes, yeah. And I said, that's it? And she said, well, it's simple. It doesn't mean it's easy. But in that moment, I suddenly realized that complexity theory had given me a way to unify my spiritual interests with my scientific interests. And very rapidly, all the rest of Buddhist metaphysics just erupted from complexity. Interdependence is how the colony is based on how every ant interacts with every other ant. And any ant changes its behavior, everything may change. Just as every community depends on every small act of every human. And you change anything you do, everything may change. And you can predict that emergence will happen, but you can't predict exactly what it is. That's karmic law. Karma doesn't mean good things happen to good people, bad things happen to bad people. It means that the next moment is dependent on what happens in this moment. And the next moment after that, and the next moment after that. How the adjacent possibles arise and then collapse down into the next moment. That's karma. There's one major thing I'm not thinking of now, but you can go to the book. It's in chapter 8, I think. And then I started discovering that the process of meditation was a way of opening these things up in an experiential way, not just a path of concepts and scholarly activity. And that's where the book comes from. And I think that's where the book comes to land ultimately. Or I hope so.
I mean, for an N of 1 as a reader, 100%. I mean, I think yes, it's experiential, every moment, and yet it's really hard to let go of the intellectual curiosity to try and put some sort of tangible concept around experience. And I think that this is it's a really it's a unique way of doing it, I think, and you don't just lay out the quantum theory and the cellular and atomic and subatomic aspects of complexity theory. You tie it directly into your own experience and into how this translates into the experience of being a human and being aware. And I think that's it's there aren't a lot of holes that kind of needed to be filled in the spiritual literature. There's a lot out there, right? It's all mostly pointing to the same thing. But I think that the marriage of scientific theory and spiritual experience is really special about the book.
Thank you. It's not what everyone needs. In Buddhism, we talk about skillful means. The teacher has to find the skillful means to teach the student. Not every student is going to respond to every way. You as a medical student responded to me in ways that other medical students did not. I was not what they all needed, but I was what some people could hear and respond to. But in our society, in our culture, where we are so immersed in this idea that the world is a machine, that we are machines, reflects all our language in Western medicine and Western biology about how we fix our bodies if there's illness or disease, etc. And there's an intuitive need amongst people in our culture that's not explaining everything. But I think it's complexity that for such people, for me, for you apparently, it provides a route. And I remember very quickly after I had that experience in the Zendo, I suddenly realized that the idea of striving to understand the true nature of reality as a spiritual practice was striving to physically, really in your gut experience the true nature that the world is a complex system arising from at least the quantum scale. What we don't have time to really talk about, although we could touch on it if you want to, but you might want to leave that for people who pick up the book, is what's the relationship of consciousness to all of this? And broadly, there are two views. Consciousness emerges from existence. Our brains make our mind. And that's the dominant cultural perspective, that if we understand the brain well enough, we'll understand how it gives rise to the human mind. But you mentioned earlier there's the hard problem of consciousness, which is, I guess we are going to discuss that. I'll try to make it fast. That the brain can, the neuroscience can explain how light bouncing off of a red rose enters your retina, causes chemical signals in the cells of the retina, which lead to an electrical impulse, which go along your optic nerve to your visual cortex in your brain, and you see the color red. But if I ask you to close your eyes and visualize a red rose, none of that is happening, and yet you have the image of a red rose in your mind, in your conscious awareness. Where is your conscious awareness? Can you feel the limits of your conscious awareness? Is it shaped like the inside of your skull? No, it's not. It's boundless. So where is that? That's the hard problem of consciousness, is how can the brain give rise to that if there's no impulse to do it? And so all of our cognitive neuroscience, all of the thousands and thousands of publications on this topic always talk about neural correlates of consciousness. They can't say that there's something in the brain that causes these experiences, only that correlate with these. The other possibility is the brain is transducing, like a radio transduces radio waves. The brain is transducing a greater mind into our limited human minds. The way radio waves are infinite in all directions, but if you sample them the right way, you get the Beatles. You don't open the radio and think you're going to see a little Beatles band playing inside it. But there's no music in the waves. It's just infinite waves. And yet somehow it gets turned by the radio into this experience. I think that's what our brains are doing. And the alternate view is that actually consciousness comes first. And modern quantum physics points at that. Max Planck, the father of quantum physics, said that what quantum physics shows is that consciousness is what underlies existence. Relativity, though Einstein really had problems with this himself, points to the same thing. Complexity theory says the same thing. The nature of things depends on your level of perspective. If you look at the body at this scale, our bodies are things. If you look at it at the cellular level, the thing disappears and it's a community of cells. Where you choose to focus determines the nature of the world. So consciousness comes first, and the universe arises from consciousness. And complexity theory supports that idea, is compatible with that idea, And when you read the stories of people who study the mind by turning the mind inwards through contemplative practice, what do they discover? That the mind is vast. The way we get a taste of when I ask you to close your eyes and look at that rose, now imagine the moon up in the sky. How far away from your skull is that? And yet it can be contained within your awareness. I ask you to imagine the universe. Your awareness can contain the universe. It's awareness that comes first. That can be unpacked in, endless confusing detail, which we could do for another hour if you wanted to at some point. I'd be happy to.
I think we're gonna have to do that. Let's do part 2.
Sure.
But we'll in the meantime, folks, go buy the book. It's worth it. Trust me. And I'm not just saying that because I looked up to Neil 20 something years ago and still do. It's worth your time. And thank you so much for doing this. We'll work on scheduling part 2 ASAP.
Terrific.
That's all for this episode. Thanks everyone for listening. And if you're looking for more, be sure to follow us on social at WildHealthMD and head over to wildhealth.com or wildhealth.com/premium to become a patient and experience precision medicine for yourself.